it's amazing. I'm the reason everybody fired up this evening. I'm exhausted, barely breathing, holding on to what I believe in. No.
Good afternoon. We are the Armstrong Globe Rollers, and today we're going to take the time out to show you a physics lesson. We're going to show you velocity of 4 objects of various mass and radii down the inclined plane at 30 degrees, 22 degrees, and 15 degrees. First, we will show you how to set up your board at the certain angles. I will now pass it to my partner, Steven. Alright, right now we have Steven setting up the board. He's measuring the height, the vertical height. And once you measure get the vertical height, you got the angle. We have the incline length, and you just cross-reference it with the formula, and make sure that's the vertical height. Before you begin your trials, you must choose 4 objects of different mass and different radii. For our experiment, we have chosen a hockey puck, a piece of plastic piping, electrical duct tape, and a red spear. Make sure you record the mass of each object and its radius before you begin your trials. And now we show you our trials for the 30-degree angle with all 4 objects rolling at one time. Okay, go. Alright, that was the first test run. We're going to do it one more time.
Just keep the eye on the finger.
No way we're gonna get those to go all down.
Yeah, we're going to try. Alright, this is trial number 2. All objects simultaneously down the pipe. And they're off. Even though they went off separate ways, individually, when you test your trials individually, they will stay on the board. Just to be patient. And the last trial, simultaneously. And they're off. Yeah. Like I said, individually trial, they will stay on the board. After we recorded our data for the 30-degree incline, we also took the incline for the 15-degree angle and 22-degree angle and had time trials for those as well. Record that time, average it out, and you will come up with a nice time for each object. Once you have done this, you will get a nice average for all 4 objects, and you can compare and contrast objects to their mass and to their radii. For our experiment, we conclude that objects with bigger mass travel down inclines faster. In this case, the biggest mass for our objects was the hockey puck. Now that you completed your calculations and your equations down the incline, it's time to move on to part 2. In this part, we will show you about mass moment of inertia. The mass moment of inertia is defined by the equation Ig equals 1/2 mr squared. We use this equation because most of our objects are, in fact, round or in the cylindrical reference. And you can find this equation in any dynamics book or any physics book. Once you have defined this equation, it is best to do it by hand, or you can do it by computer. We have a program called SolidWorks that will also calculate the mass moment inertia for the various objects if you design the parts correctly. If you take a look on the next picture, you will see our hand calculations, which include all of our work for all 4 objects: the pipe, the tape, the sphere, and the hockey puck. Now that you've seen our hand calculations, make sure you complete your own and make sure they're correct before you move on to the next phase. The next phase, you will be examining the theory behind the mass of each cylinder, its radius, and its moment of inertia, and how it relates to acceleration, which is basically a simple comparison, because the mass of the object is rotating about the z-axis. You can do the simple right-hand rule and make sure you know which axis is rotating about down the incline, and its radius is constant throughout the whole process. You can use instantaneous centers also to help find this, and it will help you calculate the moment of inertia of the object, which will later play a part in determining the acceleration of this object down the incline and its angular acceleration as well. Now it's your turn. Get out there and do your own.